Hey folks, so welcome to our rotation unit. Just as a disclaimer before you start watching this video, I am going to move my document camera around a couple times, so there's going to be some jarring visuals as I adjust the camera's focus from the paper to something I'm going to demonstrate. Rotation is the last unit of this course now, and so it's another one of those units like simple harmonic motion where we put together a bunch of things we've already learned in a new setting, and the only difference is that with rotation, it's generally a very new setting because we have different variables that we're introducing instead of simple harmonic motion, which just relied on kind of the pre-existing variables. So, introduction to rotation. Quick definition, rotation is when all the particles of an object move in circular paths around a central axis. And so any object, in theory, could rotate. I could take my pencil and I could rotate it around like this. I could take one of the rings off my finger and I could spin it and it would rotate like that. And a person can rotate. So everything can, again, in theory, rotate. In AP Physics 1, we focus on things that are rigid instead of flexible. So if I tried to rotate this piece of paper, it's actually changing its shape as I move it. Or if I took a piece of string and wiggled it, even if I spun it around a circle, not all parts of that rope are going to rotate together. One part of it at the end will lag behind the parts that are close to my hand. So the requirements for rotation in AP Physics 1 are that there's a central axis around which all particles are moving, and all the particles move in unison around that circle. And we'll describe what this means specifically once we get to our variables. And so I wanted to demonstrate that with something that we have in a classroom that you'll see in class anyway. And so here's our first jarring camera motion. That wasn't too bad. So we have this rotating platform, and I think it can focus pretty well. Cool. And so this is powered by an external power source, and so if I plug it in and set it on its way, hopefully, there we go, it will start to move. And I'm going to go, there we go. I'm going to go turn up the voltage because this is not enough. Okay, so it just required some enticing. And so now the platform is rotating. And so I just put these posts in the platform, different distances from the center, and I made them into flags. So there's the manila one for the masking tape, and then there's the blue one for the painter's tape. And so I want you to just observe this for a minute. And so we'll start here. And there's some things that are going on. So I'm gonna stop it, and then I'll start it up in another minute. If I bring these flags over here, to kind of map things out, this object is rigid, this is a plastic disc, and these posts are metal posts that are literally screwed into the platform. The central axis is right here, where the platform's screwed in, and there's basically a pulley that's run by a motor, not a pulley, a wheel that's run by a motor underneath that just uses friction to push the platform and cause it to rotate. So the important thing to notice is that the manila flag is closer to the center of this disc as compared to the blue flag. And so that's kind of what we're here to talk about. When the rotation happens, and it might take a minute to get up to speed, but as that rotation's happening, I want you to notice two things. In general, the blue flag is blurrier. More blurry, and that's because it's moving faster. So one aspect of rotating things is that even though all the particles are essentially moving together, each particle has its own specific speed. So the blue flag is moving faster than the manila flag. The other thing that's almost contradictory is that both flags get around a complete circle in the same amount of time. And so whenever you have an object that's rotating, the rotating aspect of it is uniform, but the linear aspect to it is not uniform. And so I'm going to do this by example, and the thing I'm going to show you is I can now let me line this up. So right now everything's lined up. We have the central axis, we have the manila flag and the blue flag. So this is like the initial position. Now there are like lines here, and these happen to be at the label 0 degrees. And so rotating objects, they rotate by angle is the way that we define their displacement. And we'll write this down in a minute. But if I take this platform and manually rotate it so that now 90 degrees is facing the camera, I have rotated the platform by 90 degrees. So what does that mean? That means that both flags have made the same rotation. And we call that an angular displacement, and the flags have both rotated 90 degrees. However, the manila flag moved from right here to right here, and that's a fairly short distance, right? That's like the width of my hand. But the blue flag moved from here to here. And so here's where we understand that the two flags have to move at different speeds in order to get around the disk in the same amount of time. The blue flag needs to move faster because it needs to get from here to here in the same time as it takes the manila flag to get from here to here. And so we have some relationships we're going to write down about rotating objects. I'm going to have you capture this example in a diagram that's based on this rotating platform. And so the first thing you want to do is draw a circle, and that's the platform. I drew 3 dots. 1 dot is approximately in the center of the circle, and we're going to label that axis of rotation. And I'm going to make sure that the diagram doesn't interfere with that label at all. So the platform is going to rotate, and it's going to rotate around this axis. Different objects have different axes of rotation, and if it's an object you can like hold in your hand and move around, you can actually make it rotate about several different axes, or maybe infinitely many. So what we're going to do is we're going to track the motion of point A, which is right here, and point B, which is right there. And so the way we're going to do it is we are going to imagine that we're rotating this platform in the counterclockwise direction. Oddly enough, counterclockwise is defined as the positive direction when we're talking about rotating objects. So in terms of vectors, we're going to rotate this in the positive direction. And after I rotated a certain angle, I am going to make it so that point A has now navigated itself to this location. And so we'll call this point A prime. And so let's label some things about A. So there is, I can measure this distance. A is a certain distance away from the axis of rotation. And so this is a circle, so let's label it R for radius, and it's the radius that point A is away from the center. Now, just rotating it doesn't actually change that distance, and so the value of RA is constant. I have moved point A also by a certain angle theta, and in terms of a circle, when you move displacement around a circle, it's not always just called displacement, it's called arc length. And so arc length has the variable s. Okay, so we can define some things. So r is distance from the axis. Theta is still angle, but in this case it's the displacement of that point, and then s is arc length, which is also a distance, so that's the linear distance. So arc length and displacement are the same. Okay, so we have 3 measurements that we can make about this little rotation. The distance from the axis, which is in meters, the arc length, which is the linear distance across, which is also in meters, and then angle, which for the purposes of rotation are measured in radians. Radians isn't a unit of measurement, it's a ratio. So we will use radians for this. Okay, so if that happened at point A, where's point B? And so I did something very purposeful here, and I made sure, to the best of my eyeball's ability, that the point A, the axis of rotation, and point B are all in a straight line. What that means is as point A rotates, point B rotates the same way. And so to be as accurate as possible, I'm still going to take a guess, but point B is not that far away. We're going to say that point B has now migrated to this point right there. And this is point B prime. So that's the new location at point B. I can do all those same things with point B. Both this measurement and this measurement are the distance that point B is away from the central axis. The angle of displacement is there, and what you're going to notice is that these are two straight lines that both intersect this central axis, and so these angles have to be the same. And then the arc length is going to be measured that way. So when I take the platform and I rotate it some angle, the following things happen. So when platform is rotated, the main thing I want you to see is all particles have the same, and we're going to call this angular displacement. So everything in the object is going to rotate by the same angle relative to that, no matter where it is. On the other hand, all particles have unique arc lengths or linear displacements. Or arc length. Right. And so that happens every time something rotates, that all the particles in a rigid object rotate together. So they always have the same angular properties. But not all parts of an object are the same distance away from the central axis or the axis of rotation, and so the linear displacement of each object is unique to that particle. And if you look at this diagram, it actually depends on how far it is away. The closer the point is to the axis of rotation, the less its displacement is for a certain angle. The further away, the greater its displacement is. And so the way that we work with these values is the following relationship. These three variables are mathematically related. S equals R times theta. The linear distance that a point will travel is equal to the distance it is away from the central point times the angle that it's displaced. And so you'll see there's two more equations like this in this part of the unit that deal with linear and angular variables. But again, linear displacement is proportional to angular displacement. So this is the relationship between those two variables. When something is rotating, all parts navigate through the same angle, but each part navigates through a different linear distance based on how far away it is from the central axis. And that is our first video.